Okay, let's do a slightly more difficult problem than the basic kinds we just did before. So let's keep the same setting. We've got the song lengths of pop songs in the top 40s charts, and we're assuming they're approximately normally distributed with a mean of 2.4 minutes. So something like this. What if we want to know the following? If we know that 10% of songs are shorter than a minute and a half, what's the standard deviation of the normal curve that fits our approximately normal data? So here's sort of like a picture, which is how I think about it. Conceptually, what the question is asking is, how big does the spread around the mean have to be for exactly 10% of the data to fall below this threshold? So if you imagine a very small standard deviation, most of the data is centered around the mean because there's very little spread. And then as the standard deviation gets larger, that spread kind of increases and then increases. And so you'd expect that with a small standard deviation, a very small amount of data is going to be less than 1.5 minutes. But as the spread increases, this area should be larger than this area, and this area should be larger than that area. And my pictures aren't that good, and I apologize for that. But hopefully that kind of makes sense in your head that as you widen this hump, more, and this point isn't moving, kind of more and more data is getting pushed to the edges. So conceptually, that's what's happening. It's like as you push this sort of out, there's a particular point where, maybe this is like 5% and this is like 6% and this is like 12%. So like there's some point in between for a particular spread, a particular standard deviation where that's going to be exactly 10%. And that's what we're trying to solve for. But we can't do it using just the tools of last time. Here's why. It doesn't quite fit the template for either one. To use the normal cumulative density function, that's like we know a boundary value and we're trying to find an area. And to use the inverse norm function, that's like we know what area we want, but we're trying to find the boundary value that would produce that area. Here we know both the boundary value we're interested in and we know the area that we want it to have. This is supposed to be, what did I say, 10%? So we know that 10% is supposed to be smaller than a minute and a half. The problem is we're trying to solve for the spread, but neither of these functions let us solve for the spread, so we seem to be stuck. So this is a situation where it's going to be helpful to standardize all of our data. So instead of a normal curve with a mean at 2.4, where all of our x units are minutes, let's convert them all to z-scores. Because remember, the whole idea of a z-score is it's telling you how many standard deviations is a particular song above or below the mean song length. So when you convert all of your data to z-scores, that's like taking your normal curve and you're going to shift it so that the mean that used to be at 2.4 shifts over so that the mean is at 0. And whatever the standard deviation was, you're going to stretch it or squish it so that the new standard deviation is 1, because that's kind of what it means to standardize things using z-scores. So let's remember the z-score formula. The z-score formula is z is your particular data point minus the mean value divided by the standard deviation. So that's going to come in handy later. Here, of course, we don't actually have any data, so it's not like we're going to go through a list of song lengths and apply this equation to every single song length. But here's what we can do instead. We're imagining that there's some distribution of song lengths with a mean song length of 2.4 minutes, and then 10% of the songs are less than a minute and a half. So now we're imagining, but we don't know what the standard deviation is. But we're imagining that whatever it is, if we were going to convert all of these to z-scores, the mean value would shift to 0, the spread would change, and this 1.5 minutes is going to turn into a z-score down here somewhere, and we don't know what this z-score is, but we know that there's going to be some z-score so that 10% of the data is smaller than that z-score. So here's the magic part. We couldn't use any of our functions to figure out the standard deviation up here. But down here, we've changed our problem a little bit, because down here, what we're trying to figure out is the z-score. What z-score corresponds to this boundary value that we know should have 10% of the data less than it. So now we can actually use the inverse norm function. And remember, you hit second vars to get there. Remember, the inverse norm function, what you have to give it is you have to give it the area that you want to find, you have to give it the mean, and you have to give it the standard deviation. And we can't do that up here because we don't know the standard deviation up here. But for z-scores, z-scores are this standard normal curve where we know the mean is always 0 and the standard deviation is always 1. So we know what those two are. And the area that we want is 10%, so 0.1. And so you can type all that into your calculator and it's going to give you a z-score that is this boundary value. Super cool. So when you do that, you should get that this mystery z-score is, what was it? It was negative 1.28. And then there's some other decimals of precision there. Let's stop for a second. Why does it make sense that the z-score should be negative? It makes sense because we know that this 1.5-minute song length is below the mean. And z-scores are telling you how many standard deviations above or below the mean a particular value is. So if you're below the mean, that's negative z-scores. If you're above the mean, that's positive z-scores. Okay, so how does this help us? So remember, we've got this z-score equation. So we've just figured out what's the z-score that corresponds to the boundary value we want. So you can plug that into the z-score. What else do we know? So we know the x value that's supposed to correspond to that z-score. So we can plug that in. And we know the mean of our original distribution is 2.4. And so we can plug those three values in, and now the only thing left for us to find is the standard deviation of our original function. So that's the idea. The idea is if you need to calculate either the mean or the standard deviation of an approximately normally distributed set of data, and you know a boundary value and a percentage, imagine translating it to z-scores. That changes your problem because for a standardized normal curve, you know the mean and standard deviation. And so now instead of trying to figure out the mean or standard deviation, now you're trying to find a z-score boundary, which you can do. Then you plug all the things you know into the z-score equation. So give that a try on problems S and T from the work set before, and I hope that this has been helpful.